topological invariant. So we want to talk about topological invariants. So topological invariants, they give us a way to characterize the equivalence classes of homeomorphism. In fact, one can show that homeomorphism itself is an equivalence relation. So these topological invariants are quantities that do not change under homomorphism. That's how we will define our topological invariants. So this is the definition. These are quantities, or so to say, topological invariants are quantities that do not change under homeomorphism. That means you have one topological space, but if you have a homeomorphism with some other topological space with respect to the space you started with, that means let's say you have a topological space x1 and you continuously deform it into another space. Is there any quantity that remains invariant? Those are our topological invariants. So topological invariants can be a number. So we ask what are the possible types? The possible types of topological invariants. Well, the first thing that can be a topological invariant, it can be a number. Then it can be a algebraic structure of a group. So we can say that the algebraic structure of a group and this algebraic structure has to be constructed out of the topological space, and we'll see in our later lecture when we discuss homology or homotopy. We'll see how these things comes about. So that's what we mean by an algebraic structure of a group. And even connectedness can be an invariant, just like connectedness. Compactness can also be a topological invariant, and even Hausdorff property can be a topological invariant. And the one we are going to discuss a few minutes later is a topological invariant that is known as the Euler characteristic, or so to say the Euler number characteristic, and many more. If the complete set of these topological invariants are known, then we can specify the equivalence classes by giving this invariants. So the punchline here is that, so let me write it down. The punchline here is that if two space, by two space I mean two topological spaces, if two topological spaces, okay, let me just write it down, topological spaces have different topological invariants, then they are not homeomorphic to each other. This is the punchline. So does that mean that if two spaces have the same topological invariances, or so to say the topological invariants, can we say that those two are homeomorphic to each other? Well, not necessarily. and we'll see some examples very soon when we discuss about the Euler characteristic. So this definition will work for now, and we want to see a specific example of this topological invariant, which is the Euler characteristics. So let's talk about that, and all the things that we talked about here will be more clear when we see the Euler characteristic. So now we want to talk about the Euler characteristic. And it's sometimes even called the Euler number. And before we discuss, we want to discuss examples by restraining ourselves in R3 so that it's intuitively clear as well. And this means in R3 we will only talk about polyhedrons. We will only talk about polyhedrons. So what is a polyhedron? Polyhedron can be thought of as a generalized version of a polygon. So if you think of polygon as a two-dimensional object, a polyhedron would be a three-dimensional object. Okay, and if you want to have a bit formal definition, then a polyhedron, so let me give you a small definition of a polyhedron. A polyhedron is a geometrical object that is surrounded by faces. So a polyhedron is a geometrical object that is surrounded by faces. So let me draw one. So this is an example of a polyhedron. These two-dimensional surfaces that I'm marking right now with this slightly brown color, these are our faces. There should be another one over here. So these two-dimensional surfaces are our face. So these are faces, and these are called vertices. And these lines that connect two vertices are called edges. In fact, we also call them arms sometimes, but for now we'll call them edges. So this is a structure of a polyhedron. Even a cube is also an example of a polyhedron. And now since we are done defining the polyhedron, the things that we're going to work with to compute Euler characteristics and discuss it, now let's define how do we compute the Euler characteristic, or so to say the Euler number. So this is the definition of this Euler number or Euler characteristic. So